Is Mars humanity's backup plan? Tonight, we're going to explore one of the most ambitious dreams in human history, establishing our first permanent foothold on another planet. You've probably seen the glossy renderings in documentaries, the confident timelines from tech billionaires, the romantic vision of red sunsets over gleaming domes. But here's what most people don't realize. Building even the tiniest base on Mars isn't just difficult. It's a cascade of interconnected nightmares that make Antarctic research stations look like luxury resorts. By the end of this journey, you're going to understand exactly why every single thing we take for granted on Earth becomes a life-or-death engineering challenge 140 million miles away. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This is going to be eye-opening. Imagine that we succeeded. The first habitat modules are gleaming against Mars' red and desolate horizon. Picture this moment for a second. 6 astronauts are celebrating inside a metallic structure of 200 square meters, roughly the size of 2 average apartments. They're high-fiving in their pressurized suits, grinning behind their helmet visors as Earth's cameras broadcast this historic achievement to billions watching below. The excitement is palpable. Humanity's first permanent foothold on another world. This moment of technological triumph hides an inconvenient truth that nobody wants to admit publicly at space conferences. The harsh reality that engineers whisper about in private conversations. The calculations that get buried in appendices of reports that senators never read. The uncomfortable facts that get glossed over in glossy presentations about humanity's multiplanetary future. The base was already condemned from the moment it touched down, not because of any engineering failure, but because of the implacable physics of a dead planet. And every single system keeping those 6 people alive is fighting a battle against forces that have been winning for 4 billion years. You see, Mars isn't a blank canvas waiting for colonization. It's a cosmic trap disguised as an opportunity. The red planet that looks so inviting in those artist renderings, so similar to Earth's deserts, is actually an alien world that operates by rules completely hostile to everything your body needs to survive. Let me put the Martian atmosphere in perspective for you. It has just 0.6% of Earth's pressure. Think about this. If you've ever felt short of breath at high altitude, maybe climbing in the mountains, you've experienced what happens when air gets thinner. Your lungs work harder, your heart beats faster. You feel that struggle for oxygen. Now imagine that feeling multiplied by a factor of 10. It's like standing on top of Mount Everest, except the Everest comparison doesn't even come close to capturing the brutality of what Mars offers. Trying to breathe on Mars without protection would be exactly like opening the door of a spacecraft in orbit. Instant death. Your saliva would literally boil on your tongue as the moisture in your lungs expanded explosively. The vacuum would pull every molecule of air from your body in seconds. This isn't science fiction drama. It's basic physics playing out in the most unforgiving way possible. The temperature averages minus 63 degrees Celsius. To help you visualize what that means, water doesn't just freeze at that temperature. It becomes a rock-hard substance within seconds. Metal becomes so brittle, it can snap like a pretzel. Rubber seals and gaskets that work perfectly on Earth turn into crumbling fragments that offer no protection whatsoever. Now, you might think, well, Antarctica gets to minus 60 degrees, and we have research stations there. Here's the crucial difference that changes everything. In Antarctica, you still have a breathable atmosphere around you. The air is thin and cold, but it exists. You can breathe it. You can hear sounds traveling through it. The pressure supports your body's basic functions. On Mars, you have an almost perfect vacuum. The difference between Antarctic cold and Martian conditions is the difference between a challenging camping trip and immediate suffocation in an alien wasteland. But the invisible killer is far worse than the cold. Cosmic radiation bombards the surface with 0.67 sieverts per year. This number might not mean much to you, so let me translate it into human terms. That's 240 times higher than the annual dose considered safe on Earth. To put this in context, workers at nuclear power plants, people whose job involves being around radiation, receive at most 0.02 sieverts annually. That means a person living on Mars would absorb 30 times more radiation than someone whose profession is literally handling radioactive materials. Think about that for a moment. The background radiation on Mars is more dangerous than working directly with nuclear fuel rods on Earth. This radiation doesn't just increase your cancer risk. It tears through your DNA like invisible bullets, creating damage that accumulates day by day, hour by hour. Every breath you take on Mars brings you closer to genetic destruction that your body simply cannot repair fast enough. The gravity seems like it might be helpful at first. At 38% of Earth's pull, you'd weigh much less, move more easily, jump higher. But your body didn't evolve for this. Your muscles and bones have been shaped by billions of years of evolution under Earth's specific gravitational force. Remove that force, and your body begins to cannibalize itself. Your muscles and bones lose 1 to 2% of their mass every single month. It's like being forced to age at the rate of an 80-year-old, but 10 times faster, with no possibility of complete recovery. Your skeleton, which has supported you your entire life, begins dissolving from the inside out. Calcium leaches from your bones into your bloodstream, creating kidney stones and weakening the very framework that keeps you upright. Then there's the soil itself, the regolith that covers Mars like a poisonous blanket. It contains compounds called perchlorates, which are chlorine and oxygen molecules that destroy human thyroid function in small doses. A single teaspoon of Martian soil has roughly the same toxicity as drinking diluted bleach. You couldn't grow food directly in it, even if you could somehow solve the water and temperature problems. The dust is electrostatically charged, meaning it clings to everything with an almost magnetic persistence. These particles are 3 micrometers in diameter, smaller than red blood cells. They slip through filters designed to keep them out, work their way into every crack and crevice of spacesuits and mechanical systems, and if inhaled, they perforate lung tissue like microscopic needles. During global dust storms that can last for months, solar panels become completely covered. Energy production doesn't just drop, it collapses by 99%. The 2018 storm that killed the Opportunity rover blanketed a quarter of the planet for more than 3 months. Imagine your life support systems running on backup power for that entire time, with no possibility of recharging, watching your battery reserves tick down day by day. Here's something that sounds impossible, but is absolutely true. Liquid water cannot exist on the Martian surface. Water needs a pressure of at least 611 pascals to remain liquid at any temperature. Mars provides only 600 pascals. It's always just below the minimum threshold. So water either evaporates instantly into the thin atmosphere or freezes solid. It never maintains that precious liquid state that every biological process requires. This means that any water system outside your habitat will fail. Pipes burst when the water inside them turns to ice in seconds. Emergency water supplies left outside become useless blocks of ice, harder than concrete. Even a small leak in your water recycling system becomes catastrophic because the water won't stay liquid long enough for you to contain it. Any leak in the habitat instantly exposes the crew to this partial vacuum where their saliva would begin boiling on their tongues before they lost consciousness. In 15 seconds of exposure, their lungs would collapse as the air rushed out of their bodies. Blood vessels would dilate catastrophically as dissolved gases formed bubbles in their bloodstream. Brain death would occur within 90 seconds if they weren't rescued immediately. The life support systems have to work perfectly 24 hours a day for 687 Earth days that make up a Martian year, with absolutely zero margin for error. A 10-minute failure in oxygen supply or pressurization kills everyone aboard. There's no plan B, no evacuation route, no emergency exit. You can't step outside to fix a problem. You can't call for help from the neighbors. If something goes catastrophically wrong, rescue from Earth takes a minimum of 7 months when the planets are aligned favorably and 26 months when they're on opposite sides of the Sun. Communication has a delay of 4 to 24 minutes in each direction, making real-time conversations physically impossible. You can't call home for help and get immediate advice. When you ask Mission Control how to fix a critical failure, you wait 24 minutes for their response, and by then it might be too late. Emergency supplies must be sent from Earth 2 years in advance, making perfect launch timing a matter of life and death. Every backup part, every redundant system, every spare component must be planned and shipped before you even know you'll need it. There is no overnight delivery to Mars, no emergency supply runs, no possibility of improvising with materials that simply don't exist on a barren world. Transportation costs of $2 million per kilogram make every spare screw more valuable than gold on Earth. Think about that. Every single component in your habitat costs more than most people's homes just to transport there. A simple wrench costs $40,000 to deliver. A replacement computer chip costs $200,000. The economic reality makes every piece of equipment irreplaceable. The most basic Martian base requires 100 tons of equipment with an initial budget of $200 billion just to exist. And this is where the dream starts to poison itself, because all of this infrastructure, all of this incredible complexity and expense still leaves you trapped in a tiny metal box, surrounded by a world that wants to kill you in dozens of different ways, every single second of every single day. The 6 astronauts celebrating in that habitat aren't pioneers opening a new frontier. They're survivors clinging to life in the most hostile environment imaginable, completely dependent on systems that must never, ever fail. And this is just the beginning of understanding why building even the smallest base on Mars isn't just difficult. It's a cascade of interconnected nightmares that make Antarctic research stations look like luxury resorts. Every breath they take is filtered and recycled. Every drop of water they drink has been processed through their own waste. Every calorie they consume was shipped from Earth at enormous cost. They aren't living on Mars. They're barely surviving in a technological bubble that could pop at any moment, leaving them exposed to forces that have kept Mars lifeless for billions of years. And that technological bubble is sustained by numbers that reveal just how precarious this entire venture truly is. Let me walk you through the brutal mathematics of survival that engineers calculate in spreadsheets but rarely discuss in public presentations. Each astronaut needs 0.84 kilograms of oxygen per day just to breathe, plus 2.3 kilograms of water for drinking and basic hygiene. These aren't negotiable amounts. They're the minimum requirements for keeping a human being alive. 6 people consume 5 kilograms of oxygen and 14 kilograms of water daily. Over the course of a Martian year, that adds up to 1,125 kilograms of oxygen and 5,110 kilograms of water annually. Think about those numbers for a moment. That's nearly 2 tons of oxygen and over 5 tons of water every single year, just to keep 6 people breathing and hydrated. The recycling systems currently operating on the International Space Station are marvels of engineering, recovering 93% of all water used. That sounds incredibly efficient until you realize what that 7% loss means in practical terms. On Mars, that seemingly small percentage translates to 358 kilograms of fresh water needed annually. And that's assuming everything works perfectly with no emergencies or equipment failures. To extract that replacement water from the ice buried beneath Mars's surface, you need to melt it using 41.8 megajoules per kilogram. That's equivalent to 11.6 kilowatt-hours of electricity for every single kilogram of water produced. To meet that annual requirement of 358 kilograms, the base needs an additional 4,153 kilowatt-hours of energy, which is roughly the same amount of electricity that 40 Brazilian households consume in an entire month. Now here's where the energy equation becomes truly nightmarish. Solar panels on Mars receive only 590 watts per square meter, just 43% of the solar radiation that reaches Earth due to Mars being further from the Sun. That already anemic energy collection becomes catastrophic during dust storms, when solar output drops to a mere 6 watts per square meter, a 99% reduction that can last for months. The lithium-ion batteries necessary to store energy for the long Martian nights weigh 50 kilograms per kilowatt-hour of capacity. You're looking at literally tons of additional mass just to keep the lights on when the sun goes down. And remember, every kilogram shipped to Mars costs $2 million, so those batteries represent hundreds of millions of dollars in transportation costs alone. NASA has proposed a 40-kilowatt nuclear reactor as an alternative, but the solution brings its own cascade of problems. The reactor weighs 3,000 kilograms, requires uranium shielding, and needs carbon dioxide cooling systems. Its operational lifespan is exactly 10 years, after which it requires complete replacement or the mission simply ends. There are no exceptions, no extensions, no emergency repairs that can extend its life. Food presents another mathematical nightmare wrapped in the illusion of solvability. Freeze-dried foods can provide the necessary 2,000 calories per day per person, but they degrade at a rate of 5% annually under constant cosmic radiation. After 2 Martian years, equivalent to 4 Earth years, the food loses 20% of its nutritional value, creating serious risks of malnutrition even if you have enough calories. The alternative of growing fresh food requires pressurized greenhouses covering 1,200 square meters for 6 people. That's 3 times the size of the living habitat itself. Each square meter of greenhouse needs 15 centimeters of filtered regolith, covering the walls as radiation shielding, requiring tons of excavation and processing just to create growing space. The LED lighting systems needed to grow plants consume 200 watts per square meter continuously, meaning the entire greenhouse requires 240 kilowatts of constant power, more electricity than an entire residential neighborhood uses. The temperature inside these greenhouses oscillates between minus 60 degrees Celsius at night and 20 degrees Celsius during the day, forcing heating systems to work around the clock to maintain conditions where plants can survive. Every time the crew needs to venture outside for maintenance or repairs, they're putting on spacesuits that cost $12 million each and have an operational lifetime of just 25 spacewalks before mandatory replacement. Each spacewalk is limited to a maximum of 7 hours due to battery and oxygen constraints in the pressurized suits. Basic external maintenance of the base requires a minimum of 2 people for safety, consuming approximately 50 spacewalks per year just for routine upkeep. This means replacing 2 complete spacesuits annually at a recurring cost of $24 million. And that's just for the privilege of stepping outside to fix things. The base must maintain an inventory of critical replacement parts, pumps, valves, connectors, circuits, filters, seals, components totaling 15 tons of spare equipment. Storing all these parts in pressurized conditions requires 30 cubic meters of space, which represents 15% of the total habitable volume of the base. Medical care is limited to basic antibiotics, pain medications, and fundamental surgical equipment. Something as routine as appendicitis could be fatal without a trained surgeon on the crew. The constant radiation exposure increases cancer risk by 5% for every year of exposure, meaning a 4-year Mars mission carries a 20% probability of developing cancer. The DNA damage from radiation is cumulative and irreversible. Returning to Earth doesn't undo the genetic mutations acquired during the Martian stay. Your cells carry permanent scars from every cosmic ray that punched through your body, creating a biological time bomb that may not manifest for decades. Perhaps the most underestimated challenge is the psychological toll of isolation in a claustrophobic environment with the same 6 people for years. Documented simulations on Earth show interpersonal conflicts in 78% of long-duration isolation experiments. Communication with families back home is limited to videos with 20-minute delays, making natural conversations impossible and intensifying the existential loneliness. You can't call your spouse when you're having a bad day. You can't get real-time emotional support when the stress becomes overwhelming. If a crew member dies, and statistically, given all these risk factors, someone probably will, the body must be stored in a freezer or buried outside the base. The psychological trauma to the survivors is inevitable and profound, with no possibility of counseling, no way to grieve normally, no escape from the constant reminder that death is always one equipment failure away. The truly sobering reality is that this entire complex infrastructure of life support must function perfectly for years without any possibility of rapid evacuation or external rescue. Every system, every backup system, every component must work flawlessly in an environment that corrodes, freezes, irradiates, and systematically destroys everything that wasn't specifically designed to resist it. When you add up all these requirements, the energy demands, the spare parts, the food production, the medical supplies, the replacement equipment, you begin to understand why the cost projections keep climbing higher and higher. Each solution to one problem creates 3 new problems that require their own expensive solutions. And this is still just the basic mathematics of keeping 6 people alive. We haven't even begun to discuss what happens when these systems start failing, which they inevitably will. Because Mars has been waiting 4 billion years to reclaim any technology that dares to challenge its dominance, and it has never lost that battle. When faced with these overwhelming challenges, engineers propose seemingly obvious solutions that sound reasonable in conference rooms, but crumble under the weight of Martian reality. The most common proposal is building underground bases to escape the radiation, a solution that appears so logical that you might wonder why anyone would even consider surface habitats. Here's why that apparently sensible idea becomes a nightmare of its own. Digging just 5 meters deep into Martian regolith requires drilling equipment weighing 8 tons and consuming 500 kilowatt-hours per meter of excavation. To put that energy consumption in perspective, 500 kilowatt-hours is what an average Brazilian household uses over 15 entire days of normal living. The regolith behaves like frozen concrete below 1 meter depth, the standard excavation equipment that works perfectly on Earth, bulldozers, backhoes, even industrial earth movers, would break within minutes of operation on Mars. The permafrost isn't just hard, it's harder than many types of rock, compressed and frozen for millions of years into a substance that laughs at conventional digging tools. The tungsten carbide drill bits necessary to penetrate this iron-hard layer cost $50,000 each and wear out after drilling just 10 meters. Think about that economics for a moment. Every 10 meters of tunnel requires a new $50,000 drill bit, plus the energy cost of half a month's household electricity consumption. Excavating an underground complex of 500 cubic meters requires removing 750 tons of material in an operation that would take 8 months of continuous work. 8 months of astronauts working in shifts around the clock, operating heavy machinery in spacesuits in an environment where a single equipment failure could kill everyone involved. And here's the cruel irony. During those 8 months of excavation, the astronauts would need to perform approximately 400 spacewalks of 7 hours each, exposing themselves to exactly the radiation they were trying to escape. They would absorb more cosmic radiation, building their radiation shelter, than they would save by using it. It's like trying to escape a fire by running through gasoline. The underground structure needs reinforcement to prevent collapse. Titanium beams, 3D printed concrete walls, tons of imported structural materials. Martian concrete made from regolith and frozen water has only 40% of the strength of common terrestrial concrete, meaning everything needs to be massively overbuilt to provide the same structural integrity. The ventilation system for an underground complex requires ducts 50 centimeters in diameter, drilled all the way to the surface, creating potential leak points that could catastrophically depressurize the entire facility. Each duct represents another penetration through the protective barriers you're trying to create, another point of failure in a system that cannot afford to fail. If any tunnel section collapses partially, rescuing trapped astronauts would require emergency excavation equipment that simply doesn't exist at the base. There is no fire department to call, no emergency services, no heavy rescue equipment beyond what you brought with you. Total self-sufficiency represents another illusion that engineers sell as the ultimate solution. The idea sounds perfect. Produce everything locally without depending on Earth, becoming truly independent on another world. Break the umbilical cord to our home planet and flourish as a genuine Martian civilization. But the reality of manufacturing on Mars reveals why this dream is physically impossible. Manufacturing computer chips requires clean rooms with fewer than 10 particles per cubic meter. Class 10 clean room standards. Mars has billions of particles per cubic meter constantly swirling in the atmosphere. You can't build the controlled environment necessary for electronics manufacturing when the entire planet is a dust storm waiting to happen. The contamination isn't just a minor inconvenience. Those microscopic particles destroy semiconductor fabrication at the atomic level. A single dust grain landing on a silicon wafer ruins thousands of potential computer chips. On Mars, you'd be trying to maintain laboratory-clean conditions while living inside a planetary sandblaster. Metallurgy for creating replacement parts needs furnaces reaching 1,538 degrees Celsius to melt iron, consuming 5 megawatt-hours of energy per ton of metal processed. Remember, this is on a planet where every kilowatt-hour is precious and difficult to generate. That's enough energy to power the entire base for weeks. Polymers for seals and insulation derive from petroleum or require complex chemical processes impossible without industrial facilities costing billions of dollars. These aren't luxury items. They're essential components for every gasket, every seal, every piece of flexible tubing that keeps the base pressurized and functional. Producing a single transistor from scratch requires a supply chain with 87 different steps, including mining ultra-pure silicon and processing it through multiple refinement stages. Each step demands specialized equipment, trained personnel, quality control systems, and backup processes for when things go wrong. On Earth, this supply chain spans continents and employs millions of people. On Mars, you'd need to recreate the entire global semiconductor industry with 6 people and whatever equipment you could ship at $2 million per kilogram. Lithium batteries require lithium mining, and while Mars contains lithium, it exists in concentrations 100 times lower than economically viable terrestrial mines. You'd need to process thousands of tons of Martian rock to extract enough lithium for a single battery pack, and remember, You need battery packs just to store the energy required to process the lithium. Medications have shelf lives of 2 to 5 years maximum. Manufacturing insulin or antibiotics requires bioreactors and genetically modified bacterial strains. Essentially, a complete pharmaceutical infrastructure. When someone becomes diabetic on Mars, they don't just need medication, they need an entire biotech industry. Synthesizing aspirin, the simplest possible medication, involves 6 separate chemical reactions using reagents that must either be imported from Earth or synthesized locally first. And if you're synthesizing the reagents locally, each reagent requires its own complex manufacturing process with its own specialized equipment and chemical precursors. Even glass for windows and scientific equipment requires pure quartz sand and furnaces reaching 1,600 degrees Celsius. More impossible industrial infrastructure on a world where every gram of equipment was shipped at enormous cost. The energy requirements alone would consume the base's entire power budget for days. This brings us to the ultimate engineering fantasy, terraforming. The idea of transforming Mars into a second Earth sounds like the final solution to all these problems. Make the whole planet habitable, and you eliminate the need for life support systems, radiation shielding, pressurized habitats, and complex manufacturing. The current Martian atmosphere has a mass of 25 trillion tons. That sounds like an enormous amount, until you realize it represents just 0.6% of Earth's atmospheric mass. It's like comparing a small room to a vast cathedral. The numbers sound significant until you understand the scale. To equal Earth's atmospheric pressure, Mars would need an additional 4,000 trillion tons of gases, 160 times its current atmospheric mass. That's not engineering a solution. That's manufacturing an entire planet's worth of atmosphere from scratch. Even if you could somehow release all the carbon dioxide trapped in Mars' polar ice caps and subsurface reservoirs, it would only increase atmospheric pressure to 1.2% of Earth's level. That's still 10 times less than the pressure necessary for liquid water to exist without boiling instantly on the exposed surface. Mars's gravity of 38% of Earth's means any thick atmosphere you might artificially create would slowly leak into space over millions of years. The current atmospheric escape rate is 100 grams per second. That might seem negligible, but it adds up to 356 tons lost annually with no natural process to replace it. Earth maintains its atmosphere thanks to gravity of 9.8 meters per second squared. Mars has only 3.7 meters per second squared, a fundamental and immutable difference. No technology, no matter how advanced we might imagine, can increase a planet's mass. So Martian gravity represents a permanent limitation written into the physics of the cosmos. Any dense atmosphere artificially created would leak into space over centuries, making terraforming an infinitely expensive maintenance project rather than a one-time solution. You'd need to continuously pump gases into the atmosphere faster than they escape forever. It's like trying to fill a bathtub with the drain open. The fundamental problem with all these proposed solutions is that they treat Mars as if it were a broken Earth that just needs fixing. But Mars isn't broken. It's working exactly as physics dictates for a planet of its size, distance from the Sun, and geological history. Every solution engineers propose creates a cascade of new problems that require their own expensive and complex solutions. Underground bases require massive excavation equipment that needs constant maintenance in an environment that destroys machinery. Self-sufficiency requires industrial infrastructure that would cost more than the GDP of entire nations. Terraforming requires continuously fighting against the fundamental physics of planetary atmospheres. The pattern repeats endlessly. Each answer generates more questions. Each fix demands more resources. Each technological triumph reveals 10 new impossibilities. Mars isn't resisting human colonization out of malice. It's simply operating according to laws of physics that don't care about human ambitions or engineering cleverness. And this cascade of impossibilities brings us to perhaps the most dangerous illusion of all, the belief that we can engineer our way out of problems that aren't engineering problems, but fundamental mismatches between human biology and planetary physics. Some challenges can't be solved with better technology or more money. They can only be endured at costs that grow exponentially with each proposed solution. When conventional engineering approaches fail so completely, desperation breeds extreme ideas. In 2015, Elon Musk proposed a radical solution that captured headlines worldwide: detonate nuclear bombs over Mars's polar ice caps to rapidly vaporize them. The theory seemed elegant in its simplicity. Explosions would release carbon dioxide and water vapor trapped in the ice, creating greenhouse gases that would warm the planet. A thicker atmosphere would retain solar heat, triggering a cascading greenhouse effect until Mars became habitable, at least in the simplified theory. It was the kind of bold, counterintuitive thinking that appeals to people frustrated with incremental solutions to impossible problems. Musk later clarified that he wasn't suggesting single explosions, but rather a continuous flow of detonations creating artificial mini-suns over the poles, like twin pulsing stars hanging in the Martian sky. The image is almost poetic. Humanity's technological prowess creating new celestial bodies to warm a cold world. Let me walk you through the mathematics of this proposal, because the numbers reveal something profound about human desperation when faced with impossible physics. Each 100 megaton thermonuclear explosion releases energy equivalent to 408 times 400 terajoules, the destructive power of 5,000 Hiroshima bombs concentrated into a single blast. To put that in perspective, the bomb that destroyed Hiroshima released about 84 terajoules of energy. A single 100 megaton weapon contains the destructive force of an entire nuclear war from the 1940s. The scale of violence being proposed is almost incomprehensible. The brightest phase of a nuclear explosion lasts approximately 50 seconds before dissipating, then darkness returns. For those 50 seconds, each detonation would briefly create a second sun in the Martian sky, visible from anywhere on the planet. To maintain constant heating, you would need to detonate 1,728 bombs per pole daily, totaling 3,456 nuclear explosions every single day. Think about this rhythm for a moment. That's one 100 megaton bomb exploding every 25 seconds, 24 hours a day, 7 days a week, without interruption. The timing is relentless, more frequent than a human heartbeat, each pulse representing the energy equivalent of 5,000 Hiroshima bombs. You couldn't have a conversation on Mars without nuclear explosions punctuating every few sentences. The United States currently possesses 3,700 nuclear warheads in its entire arsenal, less than what this Martian bombardment would consume in a single day. Russia has approximately 4,500 warheads. The entire global nuclear arsenal of roughly 13,000 weapons would be exhausted in 4 days of this terraforming attempt. Producing 3,456 new bombs daily would require 50 new nuclear weapons factories operating at maximum capacity, an industrial undertaking that exceeds global manufacturing capability. Currently, the world produces perhaps a dozen new nuclear warheads annually. This plan would require increasing production by a factor of 100,000. The estimated cost of fabricating a modern thermonuclear warhead is $28 million each. Multiplied by 3,456 daily bombs, that's $96 billion per day just for the weapons. To maintain production for a year would cost $35 trillion, roughly 40% of global GDP devoted entirely to building bombs to throw at Mars. Transportation costs add another layer of impossibility. Each warhead weighs roughly 200 kilograms. Shipping 3,456 bombs daily means launching 200 kilograms of nuclear weapons to Mars every single day. At current launch cost of $2 million per kilogram to Mars, that's $1.4 billion daily just in shipping, before factoring in the specialized containment and safety systems required. The total transportation cost would be an additional $250 billion per day in rocket launches. Maintaining this pace for just 1 week would cost $2.4 trillion, more than Italy's entire annual GDP devoted to a single week of planetary bombing. But money represents the smallest problem compared to the physics. Nuclear explosions in Mars's thin atmosphere don't concentrate heat the way they do on Earth. Without a dense atmosphere to trap thermal radiation, 90% of the explosion's heat radiates directly into space within seconds. On Earth, our thick atmosphere traps heat and creates those iconic mushroom clouds that rise kilometers into the sky. The atmosphere acts like a blanket, holding the thermal energy and distributing it across the surrounding area. On Mars, the energy dissipates almost instantaneously with no lasting thermal effect. It's like trying to warm a house by setting off fireworks in the yard. Spectacular for a moment, then nothing. The thin Martian atmosphere provides no thermal mass to retain the heat. A 2018 study published in Nature Astronomy calculated that all the carbon dioxide available on Mars, if completely released, would only increase atmospheric pressure to 1.2% of Earth's level. That includes every molecule of CO2 trapped in polar ice, underground reservoirs, and absorbed in surface minerals. The maximum possible warming would be 10 Kelvin or 10 degrees Celsius, leaving the temperature still 53 degrees below zero. Completely insufficient for habitability. Even if the nuclear bombardment perfectly released every available gas molecule, Mars would remain a frozen wasteland. To create a significant greenhouse effect, you need at least 30 kilopascals of atmospheric pressure. Mars currently has 0.6 kilopascals available, even if you could somehow release every molecule of trapped gas. The deficit is so enormous that no amount of explosive force can bridge it. Nuclear bombs don't create new gases. They only release carbon dioxide that already exists, and this would rapidly refreeze at the poles without constant heating. You're not adding matter to the planet, just temporarily moving it from solid to gaseous form. The radiation from these explosions would contaminate the polar regions with plutonium-239, which has a half-life of 24,000 years. This would render the polar ice completely unusable for future water extraction, eliminating one of Mars's most valuable resources for any subsequent colonization attempts. Plutonium dispersed across the planet would mix with the regolith, creating permanent radioactive zones where future bases couldn't be constructed. You'd be poisoning the very planet you're trying to make habitable, creating dead zones that would persist for hundreds of human generations. The dust particles lifted by thousands of nuclear explosions would create massive clouds that block sunlight, causing nuclear winter, the exact opposite of the intended warming effect. This phenomenon has been demonstrated in terrestrial climate models, where stratospheric dust reduces global temperature by 8 degrees per decade. Ironically, the nuclear bombardment designed to warm Mars would likely cool it instead. The dust clouds would create a planet-wide volcanic winter effect, blocking solar radiation more effectively than any natural Martian dust storm. Scientist Casey Handmer calculated that the energy required to terraform Mars is 10 million times greater than the energy released by the largest bomb ever constructed. The Soviet Tsar Bomba of 50 megatons, detonated in 1961, would need to explode 10 million times to reach the minimum energy threshold for partial terraformation. Physicist Brian Toon from the University of Colorado declared with remarkable scientific understatement that exploding bombs is not a good idea for terraforming. The academic restraint in that statement barely conceals the scientific community's bewilderment at the proposal. Alexander Bloshenko from the Russian space agency Roscosmos calculated that the plan would require 10,000 heavy rocket launches, a complete logistical impossibility given that humanity manages perhaps 50 heavy launches annually across all space programs. Even if this nuclear bombardment worked perfectly, the warming would last only as long as the explosions continued. Stop the bombardment, and the planet would refreeze within months, returning to its natural state. You'd need to maintain nuclear bombardment forever. But here's what's most revealing about this proposal. It represents the moment when human ambition encounters the immutable laws of physics and responds with pure desperation. When engineering solutions fail, when mathematics proves impossible, the instinct is to apply more force, more violence, more energy. The nuclear option reveals our species' tendency to believe that any problem can be solved with sufficient application of power. We've split atoms, we've harnessed the energy of stars, so surely we can reshape an entire planet to our needs. Yet Mars remains indifferent to human willpower. The planet operates according to gravitational dynamics established 4.5 billion years ago. Its thin atmosphere isn't a design flaw to be corrected. It's the inevitable result of its mass, its distance from the Sun, and its geological history. The proposal to nuke Mars into habitability is like trying to make the ocean less salty by adding fresh water. The scale mismatch is so enormous that the attempted solution becomes absurd. Every calculation reveals the same pattern. Human engineering operating at scales that seem impressive on Earth become insignificant when measured against planetary forces. A 100-megaton nuclear explosion represents the pinnacle of destructive technology, yet it's a barely perceptible whisper against the thermal dynamics of an entire world. This is where hubris meets humility in the starkest possible terms. We've become so accustomed to bending our environment to our will that we imagine the same approach will work on alien worlds. The nuclear bombardment plan isn't just impractical. It's a symptom of our refusal to accept that some places in the universe simply weren't meant for human habitation. Mars isn't a broken Earth waiting for repair. It's a different kind of world entirely, one that operates by rules that make human survival not just difficult, but continuously expensive and dangerous. When you propose detonating thousands of nuclear weapons to make a planet livable, you've moved beyond engineering into the realm of planetary violence. You're not terraforming, you're trying to beat a world into submission. And this brings us to perhaps the most uncomfortable truth about Mars colonization. The problem isn't lack of human determination or insufficient technology. The problem is that we're fighting against fundamental physical limitations that no amount of force can overcome. The nuclear proposal reveals the desperation to turn Mars into a habitable world using brute force, while ignoring that the problem isn't lack of will, but fundamental physical limits. But even if we could somehow overcome the impossible logistics and catastrophic side effects of nuclear bombardment, we'd still face a deeper wound that has been bleeding Mars dry for billions of years. The planet's missing magnetic field represents perhaps the most insurmountable challenge to making Mars truly habitable. Earth possesses a robust magnetic field ranging from 25 to 65 microteslas, generated by an outer core of liquid iron spinning at depths of 3,000 kilometers below our feet. This invisible magnetic field extends 58,000 kilometers into space, creating a protective bubble called the magnetosphere that deflects solar particles away from our planet. The solar wind travels at 400 kilometers per second from the Sun, carrying high-energy protons and electrons that would destroy any life exposed directly to them. Earth's magnetosphere channels these particles toward the poles, where they collide with our atmosphere to create the aurora borealis, a visual spectacle that's actually planetary protection in action. Mars once had a strong magnetic field 2 billion years ago, when its core was still hot and liquid like Earth's is today. But the Martian core cooled and solidified completely, shutting down the internal magnetic dynamo that had protected the planet's primitive atmosphere. When the magnetic field disappeared, the solar wind began stripping oxygen and nitrogen atoms directly from the Martian atmosphere. The atmospheric loss rate accelerated from 10 grams per second to 100 grams per second once the magnetic protection was removed by core solidification. Over the following 500 million years, the solar wind stripped away 99% of the original Martian atmosphere. Think about that time frame. For 500 million years, Mars slowly bled its breath into space, molecule by molecule, with no way to stop the hemorrhaging. Today, only tiny remnant magnetic fields of 10 to 30 nanoteslas remain in the ancient crust, 1,000 times weaker than Earth's field. Ironically, a 2020 study revealed that these weak fields actually accelerate atmospheric loss rather than providing protection, making the situation worse instead of better. The weak magnetic field lines are easily pushed around by the solar wind, creating direct pathways for ions to escape above Mars' night side. Atmospheric loss with a weak field is 6 times greater than with no field at all, the worst possible scenario for maintaining any atmosphere. NASA's MAVEN mission has been measuring Mars's current atmospheric loss with high-precision instruments since 2014, continuously monitoring this planetary death spiral. During solar storms, when the solar wind intensifies, the atmospheric escape rate increases tenfold temporarily before returning to its already devastating baseline. The young sun was 30% more active than it is today, producing violent solar storms that accelerated Martian atmospheric erosion even further. Mars was being sandblasted by solar particles at a time when it needed to retain every molecule of atmosphere to remain habitable. Even if we could somehow create a dense artificial atmosphere without a magnetic field, it would simply leak away again over millennia. Any terraforming effort becomes an exercise in futility, continuously pumping gases into an atmosphere that's bleeding into space. NASA proposed in 2017 creating an artificial magnetic shield at the L1 Lagrange point between Mars and the Sun. This shield would need to generate a magnetic field of 1 to 2 teslas, 20,000 times stronger than Earth's magnetic field, using gigantic superconducting coils. The proposed inflatable structure would weigh 50 tons and require 10 megawatts of continuous electrical power just to maintain superconductivity in the coils. The estimated cost for construction and launch of this space-based magnetic shield is $800 billion for the basic initial infrastructure alone. The shield would need to be positioned 320,000 kilometers from Mars, requiring a propulsion system to maintain stable position against variations in solar pressure. It's essentially a satellite the size of a small space station, floating in the void between Mars and the Sun, protecting an entire planet. If the shield fails for any reason, the artificially created atmosphere would begin escaping immediately with no possibility of rapid corrective intervention. You can't exactly send a repair crew to fix a satellite floating hundreds of thousands of kilometers from Mars. The estimated lifespan of superconducting coils in space is 30 years before radiation degradation requires complete replacement. Maintaining the shield would require dedicated space missions every 5 years, with operational costs of $20 billion per decade perpetually. Here's the comparison that puts this in perspective. Mars's gravity of 38% is immutable, a permanent characteristic written into the planet's mass. But the absent magnetic field could theoretically be replaced artificially, though at prohibitive cost that makes the nuclear bombardment look economical. Even with a perfect magnetic shield functioning flawlessly, atmospheric recovery would take thousands of years of continuous gas replenishment. Earth takes 100 million years to replace its complete atmosphere through volcanism and geological outgassing, processes that Mars lacks entirely. The realistic solution would be accepting that Mars will never have a breathable atmosphere, and any colonization would be permanently dependent on artificially pressurized habitats. This isn't engineering pessimism, it's acknowledging physics. The magnetic field problem exemplifies a larger category of challenges, fundamental physical limitations that no engineering can overcome, only circumvent temporarily at astronomical costs. We're not facing technical hurdles that better engineering can solve. We're confronting the basic laws that govern how planets work. Understanding Mars's magnetic history reveals the planet's tragic biography. 4 billion years ago, Mars was a warm, wet world with a protective magnetic field, possibly harboring life in its rivers and lakes. As the planet's core cooled past a critical threshold, the magnetic dynamo shut down permanently. Without magnetic protection, the atmosphere began its inexorable escape to space. Temperatures plummeted, water froze or evaporated, and Mars transformed from a potential cradle of life into a frozen wasteland. This wasn't a sudden catastrophe. It was a slow death over geological time. For hundreds of millions of years, Mars gradually suffocated as its atmosphere thinned, its water disappeared, and its surface became the radiation-scoured desert we see today. The missing magnetic field isn't just an inconvenience for future human colonists. It's the signature of planetary death. Mars died 4 billion years ago when its core solidified. Everything we see today is just the preserved corpse of a world that once might have lived. When we propose artificial magnetic shields or nuclear bombardment or underground cities, we're essentially trying to perform technological necromancy. We're attempting to resurrect a dead world through pure engineering force. But planets aren't machines that can be repaired when they break down. They're complex systems governed by physics, chemistry, and geology, operating over billion-year timescales. Mars's missing magnetosphere represents something profound about the nature of habitability in the universe. Planets need to maintain a delicate balance of conditions over geological time to remain habitable. Earth has been extraordinarily lucky. Our planet has maintained its magnetic field for billions of years through a combination of size, composition, and thermal history that we're only beginning to understand. Mars lost that lottery. The magnetic field isn't just missing, it's permanently gone, unless we're willing to commit to maintaining artificial substitutes for thousands of human generations. That's not planetary engineering. That's planetary life support that could never be turned off. And this brings us face to face with perhaps the hardest truth about Mars colonization. Some problems can't be solved, only managed at costs that grow forever. The missing magnetic field is a wound that will never heal, a planetary condition that makes every other challenge exponentially more difficult. The magnetic field problem exemplifies a category of fundamental physical limitations that no engineering can overcome, only work around temporarily at astronomical costs. This pattern of illusory solutions extends to what many consider Mars's greatest asset: water. Martian orbiters have detected water ice in the planet's subsurface, a discovery celebrated as if it automatically solved the challenges of colonization. The Marsis radar on Mars Express found ice deposits 7 kilometers thick beneath the North Polar ice cap in 2018. Scientists estimate that 5 million cubic kilometers of ice exist on Mars, a volume equivalent to 1.6 times all the ice in Greenland. That sounds like incredible abundance until you examine where this ice is located and what would be required to extract and use it effectively. The majority of Mars ice sits in polar latitudes above 60 degrees north and south, where temperatures remain permanently at minus 125 degrees Celsius. Working in such conditions would be like trying to operate heavy machinery in Antarctica's worst winter, except with no atmosphere to breathe and deadly radiation constantly bombarding everything. The cold at these latitudes isn't just uncomfortable, it's machinery destroying, making metals brittle and electronics unreliable. Even the ice in more temperate equatorial latitudes lies buried 1 to 3 meters deep beneath protective layers of dry regolith. This isn't surface ice you can simply scrape up. It's permafrost locked beneath layers of contaminated soil that must be excavated. Drilling 2 meters through frozen regolith to reach ice requires heated drilling equipment consuming 3 kilowatts per hour of continuous operation. To put that in perspective, that's enough electricity to power 3 average homes while you're digging a hole. To extract 1,000 liters of water daily for 6 astronauts, you'd need to drill a new 2-meter well every week as the local ice becomes exhausted. You're not mining water from a single source. You're constantly moving your operation as each pocket of ice is depleted. That's just to reach the ice. Melting ice at minus 60 degrees Celsius into liquid water at 20 degrees consumes 41.8 megajoules per kilogram, equivalent to 11.6 kilowatt-hours of electricity per kilogram of water produced. A melting system for 1,000 liters daily would consume 11,600 kilowatt-hours, the same energy that 100 Brazilian households use in an entire month. Think about that energy requirement for a moment. You need the electrical output of a small power plant just to melt enough ice for 6 people's daily water needs. But the extracted water isn't pure. It contains dissolved perchlorates from the surrounding regolith at concentrations of 0.5% by mass, levels toxic to humans. Perchlorates destroy thyroid function and cause reproductive problems even in tiny amounts. Removing perchlorates requires multi-stage reverse osmosis systems with 75% efficiency, meaning you discard 250 liters of contaminated water daily for every 750 liters of clean water produced. You're literally throwing away a quarter of the water you worked so hard to extract and melt. The purified water must be chemically tested before consumption, using spectroscopic analysis equipment costing $500,000 and weighing 80 kilograms. Every drop of water must be analyzed for contamination before anyone can safely drink it. Water storage reservoirs require constant heating to prevent refreezing, consuming an additional 5 kilowatts per day. The plumbing between extraction sites and the base must be thermally insulated and heated, requiring 2 kilowatts per 10 meters of pipeline. If the heating system fails during a Martian night at minus 90 degrees, water freezes inside pipes within 8 minutes and bursts the plumbing. Your entire water distribution system can be destroyed by a single equipment failure on a cold night. Martian ice also contains trace amounts of ammonia, a nitrogen compound that causes nausea in low doses and nervous system damage in higher concentrations. Separating ammonia from water requires distillation at 100 degrees Celsius, an energy-intensive process adding another 8 kilowatt-hours daily to the consumption. Water from ancient comet impacts billions of years ago brought heavy isotopes like deuterium in proportions 5 times greater than terrestrial water. This isn't a minor contamination. It's a fundamental alteration of water's molecular composition. Drinking water with elevated deuterium causes heavy water poisoning over weeks, gradually reducing cellular mitochondrial function by 30%. Your cells literally start failing as the heavy water interferes with basic biochemical processes. Separating deuterium from normal hydrogen requires isotopic centrifugation, nuclear enrichment technology adapted for water treatment. You need uranium enrichment equipment just to make Martian water safe for long-term consumption. Even with all of Mars's water available, there's no way to create liquid oceans on the surface due to permanently insufficient atmospheric pressure. Water exposed to 0.6 kilopascals of pressure boils even at 0 degrees Celsius, transforming directly into vapor without maintaining a stable liquid phase. This means you can't have lakes, rivers, or any surface water bodies. Any water exposed to the Martian atmosphere instantly begins transitioning to vapor, regardless of temperature. Artificial pressurized lakes would need to exist inside giant domes 500 meters in diameter, requiring infrastructure costing trillions of dollars per reservoir. You'd essentially be building massive enclosed aquariums to contain what should be the most basic component of any habitable environment. The alternative would be natural underground lakes 2 kilometers deep, where pressure from overlying regolith keeps water liquid. Accessing these deep aquifers requires drilling 2,000 meters down, technology comparable to terrestrial oil wells that cost $80 million per drilling operation. At those depths, you're not just extracting water, you're conducting major geological excavation through the layers of rock and permafrost. Each drilling operation requires specialized equipment, expert geologists, and massive energy expenditure. Extremophile microbes from Earth could theoretically survive in these deep Martian aquifers, but they would contaminate pristine environments before we could detect them. Any drilling operation risks destroying the very environments we want to study. If native Martian life exists in deep aquifers, human water extraction would destroy unique habitats before we could study potentially alien organisms. We might be eliminating the most important discovery in human history just to get drinking water. Planetary protection protocols prohibit contaminating Martian environments with terrestrial microbiology until we definitively prove the absence of native life. This creates an impossible catch-22. We can't safely extract water without confirming Mars is sterile, but we can't explore for life without risking contamination. The water extraction process reveals the cruel paradox at Mars's heart. The planet theoretically has enough water for millions of people, but practical access is so complicated that each liter costs thousands of dollars in energy and infrastructure. Every liter of clean, safe drinking water requires drilling equipment costing hundreds of thousands, heating systems consuming enormous energy, purification technology requiring nuclear-grade centrifuges, chemical testing equipment worth $500,000, heated storage and distribution systems running constantly. The economic calculation is staggering. By the time you factor in equipment costs, energy consumption, replacement parts, and operational complexity, it would be cheaper to ship bottled water from Earth. The abundant water on Mars is like discovering oil deposits at the bottom of the ocean. Technically there, practically accessible, only at costs that make bottled water from Earth seem economical. Water represents the perfect metaphor for Mars colonization's fundamental delusion. We discover something that exists on the planet and immediately assume it solves our problems, without calculating what extracting and using it actually requires. Mars has water, but accessing it demands more energy than the base produces, more equipment than it can carry, more expertise than 6 people possess, and more money than nations can afford. The abundance is real and completely irrelevant. This pattern repeats with every Martian resource. Carbon dioxide in the atmosphere, metals in the regolith, energy from sunlight. Everything exists in forms so dilute, so difficult to process, so energy-intensive to extract that the cure becomes more expensive than the disease. The water illusion exemplifies how Mars seduces us with apparent solutions that dissolve under examination. We see headlines about vast water reserves and imagine our problems solved without understanding that water buried under meters of frozen rock and contaminated with toxins isn't the same as water flowing from a tap. Each discovery of Martian resources generates new waves of optimism that ignore the energy, equipment, and expertise required to make those resources useful. We're discovering ingredients for a recipe while ignoring that we lack the kitchen, the tools, the power supply, and the skill to cook. Mars offers us the cruel paradox of abundance that might as well be scarcity. Water everywhere, but not a drop to drink without building industrial infrastructure that costs more than the GDP of small nations. The paradox is cruel. Mars has water sufficient for millions of people theoretically, but practical access is so complicated that each liter costs thousands in energy and infrastructure. But even if you could somehow solve the water extraction nightmare, there's an invisible assassin on Mars that makes every other challenge look manageable by comparison. Galactic cosmic radiation consists of protons accelerated to 90% of light speed by supernovas that exploded millions of years ago. These particles have been racing across the galaxy for eons until they finally collide with Mars, each one carrying energy of 100 million electron volts. To put that in perspective, these are subatomic bullets traveling at nearly the speed of light, carrying enough energy to tear through any material. Think about this journey for a moment. These particles began their journey when massive stars, dozens of times larger than our Sun, reached the end of their lives and exploded with the force of 10 billion suns. The explosion accelerated protons and heavier nuclei to incredible speeds, launching them across the galaxy like microscopic cannonballs. On Earth, our magnetic field and atmosphere block 99.9% of this radiation, allowing only the highest energy cosmic rays to reach the surface. It's like living inside a protective fortress that deflects almost all the cosmic artillery being fired at us continuously. Mars receives the full bombardment. 240 millisieverts annually on the surface, which is 240 times above the 1 millisievert limit that terrestrial regulators consider safe. That's not just above the safety limit, it's in a completely different category of danger. A round-trip Mars mission of 30 months exposes astronauts to 660 millisieverts accumulated over the journey, permanently increasing their cancer risk by 5.5%. To help you understand that exposure level, a single CT scan delivers 7 millisieverts to a patient. A Mars mission is equivalent to receiving 94 full-body CT scans consecutively. Radiation has no safe threshold. Every single particle that strikes a cell can potentially cause DNA mutations that manifest as cancer decades later. It's like playing Russian roulette with every breath, except some of the chambers are always loaded. Heavy iron cosmic rays create the most devastating damage, punching through human cells and leaving trails of destruction 1,000 times denser than conventional medical X-rays. These heavy ions destroy entire DNA sequences simultaneously across multiple chromosomes, creating damage that cells simply cannot repair adequately. Your DNA is essentially the instruction manual for every cell in your body. When cosmic radiation tears through it, it's like someone firing bullets through a library, randomly destroying pages of crucial information. When engineers propose radiation shielding, the mathematics reveal another engineering nightmare. Aluminum shielding 10 centimeters thick reduces radiation by only 10%, while adding 270 kilograms of mass per square meter. Paradoxically, thin aluminum shielding actually makes radiation exposure worse. When cosmic rays collide with aluminum nuclei, they create secondary showers of neutrons that increase internal radiation exposure. It's like wearing armor that deflects bullets but creates shrapnel. A 2010 study showed that aluminum shielding less than 30 centimeters thick actually worsens radiation exposure instead of improving it. The shielding designed to protect you ends up creating more dangerous radiation inside your habitat. Martian regolith provides effective shielding. 5 meters of soil above a habitat reduces radiation by 98%. but that protection weighs 10,000 kilograms per square meter. Covering a 200 square meter base with adequate shielding requires moving 1,000 tons of material in an excavation operation lasting months. Water makes excellent radiation shielding due to its hydrogen atoms, with 2 meters of liquid water blocking 90% of high-energy protons. However, maintaining 2 meters of liquid water around a habitat requires constant heating and ultra-strong containment structures capable of holding thousands of tons of water. You'd essentially be living inside a swimming pool that never freezes, surrounded by heating systems running 24 hours a day to keep your radiation shielding from turning into useless ice. Solar particle events represent sudden radiation spikes that can kill unprotected astronauts within hours. These occur 5 to 10 times during each 11-year solar cycle, launching 100 million electron-volt protons across the solar system. During the solar storm of August 1972, radiation doses on Mars's surface would have reached 10 sieverts in 24 hours. A lethal exposure without immediate shelter. That's a dose that would kill 50% of people exposed, delivered in a single day. Emergency radiation shelters need 50 centimeters of water-equivalent shielding and must accommodate 6 people for 72 hours until the storm passes. You need a bunker within your bunker, ready to use at 30 minutes' notice. Solar radiation monitoring requires a dedicated satellite orbiting the Sun to provide 30 minutes of advance warning, just enough time to reach emergency shelter before lethal particle bombardment begins. Half an hour to get from wherever you are to your radiation bunker, or you die. Beyond cancer, radiation causes cognitive damage that's often overlooked in mission planning. Studies with mice exposed to cosmic radiation, equivalent to a Mars journey, show 30% memory loss that never recovers. This neurological damage is irreversible because adult neurons don't regenerate. Astronauts would return from Mars permanently cognitively impaired to varying degrees, their minds scarred by the journey as much as their bodies. The radiation literally damages the physical structure of brain tissue. Memory formation, decision-making, problem-solving, all these cognitive functions would be permanently diminished. Eyes are particularly vulnerable to radiation damage. Cosmic rays cause cataracts in 60% of astronauts after prolonged exposure above 200 millisieverts. Apollo astronauts reported seeing flashes of light even with their eyes closed. Individual cosmic rays passing through their retinas and creating visible sparks of light at a frequency of 1 per minute. Imagine trying to sleep while your vision is constantly interrupted by radiation-induced light flashes. The immune system weakens under constant radiation exposure. T lymphocyte counts drop by 15%, making astronauts susceptible to infections that would be harmless on Earth. A common cold becomes pneumonia in a radiation-compromised immune system. Antibiotics lose 20% of their effectiveness in irradiated patients, turning routine illnesses into life-threatening emergencies. Your body's natural defense against disease systematically breaks down under radiation exposure. Minor infections that your immune system would normally handle become medical crises. Radiation doesn't just damage biology, it systematically destroys electronics. Computer chips suffer bit flips when cosmic rays collide with microscopic transistors, randomly changing stored data. Memory error rates increase 100-fold in Martian radiation compared to Earth at sea level. Critical life support systems require triple redundancy and continuous error correction, consuming 40% of processing capacity just to maintain reliability. The computers keeping you alive must constantly fight against radiation-induced failures. Every calculation could be corrupted, every stored file potentially altered by invisible particle impacts. Radiation shielding for electronics requires massive additional weight and complexity. You need radiation-hardened processors that cost 100 times more than commercial equivalents, and perform 1,000 times slower. Here's the most insidious aspect of radiation exposure. It's a silent, invisible killer with no immediate symptoms. Astronauts don't feel the DNA damage accumulating in their cells. They don't notice their immune systems weakening or their memories degrading. The radiation damage manifests years after return to Earth, when cancers begin appearing and cognitive decline becomes undeniable. By then, the molecular damage is permanently written into their bodies. Every day on Mars, astronauts would absorb radiation equivalent to multiple medical X-rays. Every week equals several CT scans. Every month represents radiation exposure that would require months of safety monitoring for nuclear workers on Earth. The psychological burden of knowing this damage is accumulating would be enormous. Astronauts would live with the constant awareness that every moment on Mars is shortening their lives and degrading their minds. Radiation protection becomes a defining constraint on every aspect of Mars operations. You can't work outside for extended periods. You can't live in surface habitats without massive shielding. You can't operate sensitive equipment without expensive radiation hardening. Emergency protocols must account for solar storms that could deliver lethal doses in hours. Every spacewalk becomes a race against radiation exposure limits. Every system failure that prevents reaching shelter could be a death sentence. The radiation environment fundamentally changes the mathematics of human presence on Mars. Every hour outside protected areas accumulates damage. Every day reduces life expectancy. Every month increases cancer probability. Unlike other Mars challenges that might be solved with better engineering or more money, radiation represents a fundamental physical limitation. You can't negotiate with cosmic rays or engineer around the basic properties of high-energy particles. The radiation environment on Mars isn't just another engineering challenge. It's a fundamental limitation that makes human presence there inherently dangerous and temporary. You're not just visiting another planet, you're exposing yourself to an environment that systematically destroys human biology. And this brings us to a sobering realization. Radiation represents the perfect example of a problem that can't be engineered away. You can build shielding, but it's massively heavy and expensive. You can design radiation-hardened electronics, but they're slow and costly. You can create emergency protocols, but they only reduce risk, never eliminate it. Radiation is the silent, invisible assassin that has no symptoms until it manifests as cancer 10 years after returning to Earth. But radiation isn't the only way Mars betrays human physiology. The planet's gravity of 3.7 meters per second squared seems like it might be helpful at first. You'd weigh less, jump higher, and spend less energy moving around. This apparent advantage masks a betrayal that cuts to the core of human biology. Terrestrial organisms evolved under 9.8 meters per second squared of gravitational force for 3.8 billion years. Every cell in your body, every bone in your skeleton, every muscle fiber has been shaped by that specific pressure. Think about what gravity means to your body. It's not just the force that keeps you grounded. It's the constant resistance that your muscles work against, the pressure that maintains bone density, the force that shapes how your cardiovascular system pumps blood. Human bones lose 1 to 2% of their mineral density every month in reduced gravity. That's bone loss occurring 10 times faster than age-related osteoporosis in elderly people on Earth. Your skeleton, which has been your structural foundation for decades, begins cannibalizing itself. After 18 months on Mars, the duration of a round-trip mission plus surface stay, astronauts would lose 27% of bone mass in their hips and spine. This bone loss makes their skeletons as fragile as those of 80-year-old people with severe osteoporosis. Simple falls that would cause bruises on Earth result in hip fractures or spinal compression on Mars. Your skeleton, which has supported you your entire life, becomes a liability that could shatter under stresses that wouldn't even register as concerning in normal gravity. Intensive exercise for 2 hours daily reduces bone loss by only 50%. Even with perfect adherence to rigorous fitness protocols, astronauts still lose half their bone mass irreversibly. 2 hours of daily exercise, time that can't be spent on mission objectives, just to slow your body's deterioration. The calcium liberated from dissolving bones doesn't just disappear. It enters the bloodstream at concentrations of 12 milligrams per deciliter, 20% above healthy levels. This chronic hypercalcemia causes kidney stones in 30% of long-duration astronauts. A kidney stone on Mars, without surgical intervention, is essentially a death sentence. There's no emergency room, no urologist, no medical infrastructure to handle complications that are routine on Earth. What's a minor medical inconvenience on Earth becomes a life-threatening crisis on Mars. The psychological impact of watching your body deteriorate is devastating. Astronauts would feel their strength ebbing away week by week, knowing that every day on Mars brings irreversible physical decline. You're not just exploring a new world. You're sacrificing your body to do it. Muscles atrophy even faster than bones. Astronauts lose 15% of muscle mass in just 3 months, with the most severe losses in legs and lower back. The muscles that once carried you effortlessly through life begin failing under the reduced gravitational load they no longer need to support. Your legs, which evolved to carry your full body weight against Earth's gravity, suddenly have only 38% of that load to manage. Your body interprets this as a signal that all that muscle mass is unnecessary and begins breaking it down. The heart is a muscle, and it atrophies too. The left ventricle shrinks by 10% in 6 months, pumping less blood with each beat. Your cardiovascular system literally downsizes itself, assuming it no longer needs to work as hard. Your cardiovascular system adapts to low gravity by reducing total blood volume by 12%. Your body eliminates what it considers unnecessary blood plasma, permanently altering your circulatory capacity. Returning to Earth after Mars creates severe orthostatic intolerance. Blood pressure drops dangerously when standing upright, causing 40% of astronauts to faint during their first days back in normal gravity. The body you've spent months weakening on Mars suddenly faces the full force of Earth's gravity. Studies of International Space Station astronauts show that bone recovery takes 3 years minimum, and some never regain 100% of their pre-flight density. On Mars, with 38% of Earth's gravity, recovery would be even slower and more incomplete compared to zero gravity. The vestibular system in your inner ear, which controls balance, recalibrates to Martian gravity within 2 weeks, causing severe initial nausea. When returning to Earth, the system must recalibrate again, causing weeks of vertigo and disorientation after landing. Body fluids migrate toward the head in reduced gravity, increasing intracranial pressure and causing blurred vision in 60% of astronauts. The optic nerve swells under increased pressure, a condition called spaceflight-associated neuroocular syndrome that becomes permanent in 20% of cases. Your spine extends 5 centimeters on Mars due to expansion of intervertebral discs without normal gravitational compression. This extension stretches back ligaments and muscles, causing chronic lower back pain in 70% of astronauts during their first 6 months. Pregnancy and child development in Martian gravity represents an unsolved biological puzzle. Mammalian embryos require gravity for normal skeletal development. The gravitational force that shapes human development isn't optional. It's fundamental to how mammals grow. Experiments with pregnant rats in microgravity resulted in offspring with bones 30% thinner and permanently underdeveloped muscles. No mammal has ever completed an entire life cycle in reduced gravity. We don't know if human reproduction is even possible on Mars. Children born on Mars would have skeletons adapted to 38% of Earth's gravity. They would be unable to visit Earth without risking bone collapse under their own body weight in normal gravity. Their bones, evolved for Martian conditions, would be too weak to support them in Earth's gravitational field. This creates a horrific scenario. Martian-born children would be permanent exiles from humanity's home world. They couldn't withstand Earth's gravity long enough for even a brief visit. You'd be creating a subspecies of humanity permanently trapped on an alien world. The immune system depends on gravity for efficient lymphatic circulation. Without proper gravitational force, immune response to infections drops by 25%. Your body's ability to fight disease systematically weakens. Wound healing slows by 40% in reduced gravity due to decreased blood flow and compromised inflammatory response. Minor cuts that heal quickly on Earth become persistent medical problems on Mars. Even your body's ability to repair itself becomes compromised. Artificial gravity from centrifugal force could theoretically address these problems, but at enormous cost. Exercise in a centrifuge generating 1G requires 2 hours daily that can't be dedicated to work or research. 2 hours every day just to maintain basic human physiology. A centrifuge with an 8-meter radius spinning at 5. 4 rotations per minute generates artificial Earth gravity, but weighs 20 tons. It's a massive, complex structure to transport to Mars just to counteract the planet's inadequate gravitational field. The engineering complexity of artificial gravity systems adds another layer of failure points in motors, bearings, control systems. All must function perfectly, or the entire gravity generation system fails. And when it fails, human physiology immediately begins deteriorating. The fundamental paradox becomes clear. Low gravity makes construction and movement easier, but progressively destroys human health. There's no sustainable balance between operational convenience and physiological survival. Mars gravity represents a perfect example of an immutable planetary parameter that condemns any Martian civilization to perpetual physical degradation or expensive technological dependency. You can't change a planet's mass, so you can't change its gravitational field. The gravity betrayal extends beyond individual health to species survival. If humans can't reproduce normally on Mars, or if children born there can never return to Earth, you're not establishing a colony. You're creating a separate branch of humanity adapted to an alien world. These wouldn't be Earthlings living on Mars. They'd be Martians who could never come home. The reduced gravity that makes Mars seem more accessible actually creates a biological trap that permanently separates populations. The physiological effects of Martian gravity accumulate relentlessly. Every day weakens bones further. Every week reduces muscle mass more. Every month increases the gap between Martian-adapted bodies and Earth-normal physiology. Unlike radiation exposure that might be shielded or water scarcity that might be solved, gravitational effects are unavoidable consequences of simply existing on Mars. You can't engineer around the fundamental force that shapes how matter behaves. Gravity affects every biological process. Circulation, digestion, bone formation, muscle development, neural function all depend on the gravitational environment your body expects. Change that environment and everything begins to fail. The reduced gravity that initially seems like Mars' most appealing feature becomes another way the planet slowly kills human biology. Your skeleton dissolves, your muscles waste away, your cardiovascular system shrinks, and your body adapts to an environment that makes you permanently alien to your home world. The irony is profound. The very feature that makes Mars operations seem easier becomes a biological death sentence over time. What feels like an advantage is actually a slow-motion catastrophe, and this reveals perhaps the cruelest irony of Mars colonization. The planet's apparent advantages turn into long-term disadvantages that destroy the very biology they seem to help. What feels easier becomes deadly over time. Every aspect of Martian gravity conspires against human survival. It weakens bones, atrophies muscles, compromises circulation, impairs immune function, and potentially makes reproduction impossible. The gravity problem can't be solved, only managed through constant technological intervention that adds weight, complexity, and cost to every aspect of Mars operations. Gravity is the perfect example of an immutable planetary parameter that condemns any Martian civilization to perpetual physical degradation or dependence on expensive compensatory technology. When the full scale of these challenges becomes clear, the natural response is to reach for technological solutions, but this is where engineering ambition crashes headlong into economic reality. SpaceX estimated in 2016 that establishing a 6-person Martian base would cost $100 billion in optimistic projections. Independent analyses in 2021 revised that number to $500 billion when considering all support systems and realistic contingencies. To put that cost in perspective, the Manhattan Project that developed the atomic bomb cost $23 billion adjusted for inflation. A Mars base would cost 20 times more than the most ambitious military scientific project in human history. The complete Apollo program cost $280 billion adjusted for inflation and employed 400,000 people during 8 years of intensive development. Mars colonization would require nearly twice that investment just for the initial base, before considering ongoing operational costs. A permanent Martian base would require regular supply missions from Earth for decades. 4 cargo missions annually at $5 billion each means $20 billion per year in supply costs alone. That's $20 billion annually just to keep 6 people alive on another planet. The mathematics of this dependency are staggering. Over a 25-year operational period, supply costs alone would total $500 billion, equal to the entire initial construction budget. You're essentially paying for the base twice, once to build it, once to keep it supplied. The return on investment is exactly zero. Mars has no economically valuable resources that justify the cost of extraction and transport back to Earth. Martian minerals contain the same elements as terrestrial ones: iron, silicon, aluminum, nothing rare or exotic that would justify interplanetary mining. Helium-3 is often cited as a valuable lunar resource, but Mars has concentrations 100 times lower than the Moon, making extraction completely economically unviable. Even if you could mine it, transporting it back to Earth would cost more than any conceivable market value. Space tourism to Mars might generate some revenue, but tickets would cost $10 million per passenger, even in the most optimistic scenario. The total market of perhaps 1,000 millionaires willing to risk their lives for a Mars vacation represents a one-time revenue of $10 billion, a fraction of development costs. The scientific knowledge generated by a Martian base would be valuable, but intangible. Discovering extinct life forms doesn't pay the $500 billion construction debt. Consider the alternative: spending the same amount on 100 sophisticated robotic missions that could explore the entire planet without risking human lives. Rovers like Perseverance cost $2.7 billion, including launch. With a Mars base budget, you could send 185 rovers to comprehensively explore every region of Mars. These robotic missions would generate exponentially more scientific data than a single human outpost constrained by safety requirements and survival priorities. Robots can venture into lava tubes, scale cliff faces, dive into polar ice, and explore radiation zones that would kill human astronauts. Space telescopes, like James Webb, cost $10 billion and revolutionize our understanding of the universe. 50 equivalent telescopes could fit within a Mars colonization budget, advancing astronomy more than any single planetary base. The backup for humanity argument collapses under scrutiny. If Earth becomes uninhabitable through nuclear war, Mars is naturally billions of times worse for human survival. Surviving in a post-apocalyptic Earth bunker would be infinitely easier than surviving on Mars, because Earth would still have a breathable atmosphere and accessible water. Even a radiation-contaminated Earth would be more hospitable than Mars on its best possible day after impossible terraformation. Earth's worst-case scenario remains paradise compared to Mars's best-case scenario. The claim that developing Mars technology helps Earth is misleading. Perfect recycling systems cost billions to develop for Mars. The same environmental benefits could be achieved on Earth for a fraction of the cost using simpler, proven technologies. Investing $500 billion in terrestrial renewable energy would install 250 gigawatts of solar capacity, enough to power 100 million homes permanently. That same investment in medical research could cure dozens of rare diseases, saving millions of lives annually for generations. Public universities in developing countries could be funded for centuries with a Mars colonization budget. Education infrastructure that would benefit billions of people gets ignored while we fantasize about housing 6 people on a dead planet. The nationalist argument about space prestige replicates Cold War thinking without an actual adversary. China isn't racing to Mars. They're developing a sustainable space program focused on practical benefits. The moral priorities are inverted. We should resolve urgent terrestrial problems like climate change, extreme poverty, and basic education before dreaming about escaping to another planet. It's cruel irony to spend trillions trying to flee a planet damaged by humanity instead of repairing that damage for a fraction of the cost. Mars colonization represents the dreams of bored billionaires who can't afford to play with planetary-scale projects. It's not a democratic solution for humanity facing real climate crisis. It's an escape fantasy for the ultra-wealthy. The romantic vision of pioneers exploring a Martian frontier obscures the reality. Aristocrats buying tickets while billions suffer on an increasingly degraded Earth. Mars colonies would be luxury survival camps for the global elite. The perfect life support technology required for Mars could save collapsing terrestrial ecosystems, but the focus remains on abandoning Earth rather than repairing it. We're developing technology to escape environmental destruction instead of preventing it. This represents a psychology of forward flight, avoiding responsibility for terrestrial damage by fantasizing about pristine new beginnings on virgin worlds. But Mars isn't a virgin planet if it harbors subsurface microbial life. Human colonization would destroy native biospheres before we could study them adequately. The ethics of colonizing Mars without confirming the absence of life is equivalent to potentially destroying a second Genesis in our solar system irreversibly. We might be eliminating the most important scientific discovery in history for the sake of human expansion. The opportunity cost is staggering when you truly comprehend the scale. $500 billion represents the entire annual GDP of countries like Belgium or Ireland. It's more than the market capitalization of most Fortune 500 companies. It's enough money to transform entire continents. Consider what that investment could accomplish in addressing climate change. $500 billion could fund a complete transition to renewable energy for multiple developing nations, install carbon capture facilities across industrial regions, develop fusion power technology, and still have hundreds of billions left over. The same amount could revolutionize global health. It could fund malaria eradication programs, develop vaccines for neglected tropical diseases, build medical infrastructure in underserved regions, train hundreds of thousands of healthcare workers, and establish research institutes focused on diseases affecting billions. Educational transformation would cost far less. $500 billion could build universities across Africa, provide free primary education for every child on Earth, develop advanced online learning platforms, train millions of teachers, and create scholarship programs that would educate entire generations. Food security could be solved permanently. That investment could develop drought-resistant crops, build sustainable agriculture infrastructure, establish food distribution networks, and create agricultural research centers that would prevent famines for centuries. The environmental restoration possible with Mars colonization funding would be unprecedented. You could reforest entire continents, restore coral reef systems, clean polluted rivers and lakes, establish massive wildlife preserves, and develop technologies to reverse environmental damage. Yet instead of any of these transformative terrestrial investments, Mars colonization proposes spending the same amount to maintain 6 people in a technological bubble on a planet that offers nothing but hardship and slow death. The psychology behind Mars colonization reveals something troubling about human nature. When faced with complex, messy problems that require cooperation and compromise, we fantasize about clean slate solutions that let us start over somewhere else. It's the ultimate expression of privilege, having enough resources to contemplate abandoning a damaged world instead of repairing it. Mars colonization isn't about advancing human civilization. It's about escaping responsibility for the civilization we've already damaged. Mars colonization represents technological hubris, meeting economic reality, and losing decisively. The costs spiral beyond any reasonable return, the risks multiply beyond acceptable levels, and the opportunity costs represent squandered chances to solve actual human problems. When engineers propose Mars colonies, they're essentially advocating for the most expensive prison in human history. A facility where inmates pay billions of dollars to slowly die from radiation, bone loss, and psychological isolation. The resources required for Mars colonization could revolutionize life on Earth. Clean energy for billions, cures for major diseases, education for entire continents, restoration of damaged ecosystems. Instead, we contemplate spending it all to maintain 6 people in technological life support on a planet that wants to kill them. This isn't visionary thinking. It's a colossal misallocation of human resources and attention. While Earth faces existential climate threats that could be addressed for tens of billions, we fantasize about spending hundreds of billions to recreate barely functional versions of terrestrial life on an alien world. The tragedy is that Mars colonization distracts from achievable goals that would benefit humanity enormously. Clean water for everyone on Earth costs less than a single Mars mission. Eliminating malaria costs less than one supply run to Mars. Mars advocates often invoke the example of historical exploration and colonization, but the comparison falls apart under examination. European colonizers found lands with breathable air, drinkable water, and edible plants. Mars offers none of these. It's not undiscovered country. It's an actively hostile environment that requires complete life support. The psychological appeal of Mars colonization lies partly in its apparent simplicity compared to Earth's complex problems. Climate change involves coordinating global action, changing economic systems, and confronting powerful interests. Mars colonization seems like a clean engineering challenge with clear objectives, but this simplicity is illusory. Mars colonization involves all the complexity of terrestrial environmental management, plus the added burden of creating an entire life support system from scratch in an environment actively trying to kill you. The economic calculations become even more sobering when you consider scaling beyond the initial base. If supporting 6 people costs $500 billion plus $20 billion annually, supporting 60 people would require proportionally larger investments with no economies of scale. Mars doesn't offer the economic gradients that made terrestrial colonization profitable. There's no gold to mine, no spices to trade, no new markets to exploit. Every single item of value must be imported from Earth at enormous cost. The space industry promotes Mars colonization partly because it justifies massive government spending on space technology. But the same technological advancement could be achieved through less risky, more practical projects that benefit Earth directly. Mars colonization represents the ultimate example of solving tomorrow's imaginary problems while ignoring today's real ones. We fantasize about backup planets, while the one we have faces unprecedented environmental challenges that we could solve for a fraction of Mars colonization costs. The human cost extends beyond economics. Mars colonization would require selecting astronauts willing to sacrifice their health, their fertility, their life expectancy, and their connection to humanity for the privilege of maintaining technological life support on a dead world. These wouldn't be pioneers opening new frontiers. They'd be test subjects in the most expensive and dangerous human experiment ever attempted. And the data from that experiment would tell us what we already know: humans weren't designed to live on Mars. The final cost-benefit analysis reveals the ultimate futility: $500 billion to torture 6 people in a radioactive desert versus transforming millions of lives on Earth and protecting our unique biosphere. But perhaps the most profound lesson from examining Mars colonization isn't about engineering or economics at all. Mars isn't a destination. It's a mirror where we see reflected our own limitations as a species and as a technological civilization. Our obsession with conquering this hostile planet reveals a deep psychological discomfort with human finitude and individual mortality, projected onto a cosmic scale. We cannot accept that some places in the universe simply aren't meant for us. The difference between Earth's habitability and Mars' inhabitability isn't missing technology. It's 4 billion years of divergent planetary evolution that cannot be undone. Earth has active plate tectonics constantly recycling its crust, while Mars has a dead crust 50 kilometers thick that has been frozen for 3.8 billion years. Terrestrial volcanism continuously releases gases that replenish our atmosphere. The last Martian volcano erupted 2 million years ago and is permanently extinct. Earth's liquid iron core spins and generates our protective magnetic field, while Mars's core solidified when the planet cooled, irreversibly losing its primordial heat. These fundamental differences cannot be corrected by engineering. We cannot reheat a planetary core or reactivate plate tectonics on a dead world. No amount of human ingenuity can resurrect geological processes that ceased billions of years ago. Mars is a planetary cemetery, showing us that not all rocky worlds evolve to sustain life. Most die geologically over billion-year timescales, their internal fires extinguished, their atmospheres stripped away, their surfaces frozen into permanent sterility. Earth is a statistical exception. Ideal size, perfect distance from the Sun, a stabilizing moon, a durable magnetic field. Everything aligned improbably by cosmic chance. We won the planetary lottery and now fantasize about winning it again elsewhere. Seeking Earth 2.0 on Mars ignores that we already have Earth 1.0 functioning perfectly, being degraded by the same civilization dreaming of escape. The supreme irony is that a species unable to adequately manage Earth's biosphere believes it can create an artificial biosphere from scratch in a planetary desert. We treat terrestrial climate change, raising temperatures by 2 degrees, as an apocalyptic threat, yet view the 140-degree temperature difference between Earth and Mars as merely an engineering challenge. The investment necessary to reverse global warming is $5 trillion globally, one-tenth the cost of uselessly colonizing Mars. The logic is completely inverted. It's far easier to prevent the collapse of a habitable planet that's warming than to create habitability on a planet that has been frozen since the dawn of complex life on Earth. Mars teaches us humility. We are not as clever as we think we are. We cannot overcome fundamental physics with sufficient money and determination. Some challenges cannot be solved, only acknowledged and respected. The lesson Mars offers is accepting our dependence on Earth, the only viable home we will have for millennia, regardless of science fiction fantasies. The sensible alternative is investing in terrestrial sustainability, renewable energy, ecosystem conservation, and a closed-loop circular economy. Technology developed for Mars has minimal terrestrial applications. These are ultra-expensive systems designed for an environment that doesn't exist naturally on Earth. The exception is water and air recycling systems from the International Space Station, but scaling these for terrestrial use is cheaper to develop from scratch than adapt space technology. Robotic exploration of Mars should absolutely continue. Discovering planetary history and searching for past life has immense scientific value as pure knowledge. Probes cost millions instead of billions, don't risk lives, operate for decades, and generate superior scientific return per dollar invested. Curiosity has worked for 12 years, sending back terabytes of geological data. A human mission lasting 30 months would generate fewer discoveries at 100 times the cost. The Ingenuity helicopter proved flight in Mars's thin atmosphere for $500,000. The human equivalent would require billions in massive support infrastructure. Future artificial intelligence will make autonomous probes more capable than humans for exploration. They can make real-time decisions without life support requirements, venture into environments lethal to humans, and operate continuously without sleep, food, or psychological support. The long-term vision should acknowledge that Mars will eventually be visited by humans, but not permanently colonized until technology changes radically over centuries. Perhaps molecular nanotechnology will allow self-assembling habitats using local energy and materials, but that's 23rd century technology at minimum. Or extreme genetic modification could transform humans into organisms adapted to low gravity and high radiation, a profound ethical question about fundamentally altering humanity itself. Until such radical advances arrive, accepting that Mars is a scientific destination, but not a residential one, represents the civilizational maturity necessary for terrestrial survival. The final paradox becomes clear. The only way humanity could eventually colonize other worlds is first learning not to destroy the world we already have. Mars serves as a laboratory of cosmic humility, where we learn that the universe doesn't exist to serve human aspirations. And that's perfectly fine. Every parameter that makes Mars hostile, its size, distance from the Sun, geological history, atmospheric composition, represents immutable physical reality. These aren't problems to be solved, but conditions to be acknowledged. The red planet forces us to confront our species' tendency toward technological hubris. We assume that any challenge can be overcome with sufficient engineering, sufficient funding, sufficient determination. Mars laughs at such assumptions with the silence of a world that has been dead for billions of years. When we examine Mars honestly, we discover that habitability isn't a right to be claimed, but a gift to be cherished. Earth's biosphere isn't humanity's birthright, but an extraordinary cosmic accident that created conditions for complex life. Mars colonization fantasies reveal our difficulty accepting limits. In a culture obsessed with growth, expansion, and overcoming obstacles, Mars represents the ultimate frontier, a place where human willpower meets immutable physics and loses. The romantic appeal of Martian pioneers obscures the reality of what we're actually proposing, spending unprecedented resources to condemn people to slow death in technological isolation. It's not heroic exploration, but expensive suicide. Mars shows us that some dreams are worth abandoning in favor of better ones. Instead of fantasizing about escape to hostile worlds, we could commit to making our habitable world more livable for everyone. The red mirror of Mars reflects back our fears about terrestrial environmental destruction, our guilt about damaging the only biosphere we know exists, and our desperate hope that technology can solve problems created by technology. But Mars also offers a path toward wisdom. Accepting that we belong on Earth doesn't represent failure of imagination. It represents maturity of understanding. Some limitations aren't meant to be transcended, but accepted as part of what makes us human. Mars forces us to confront the uncomfortable truth that the universe operates according to its own rules, not human preferences. Planetary physics doesn't care about our dreams of expansion or our fear of terrestrial environmental collapse. The cold mathematics of orbital mechanics, atmospheric pressure, and gravitational fields remain stubbornly indifferent to human ambition. Mars will continue its 687-day orbit, maintain its 38% gravity, and lose atmospheric molecules to space, whether humans approve or not. This indifference isn't cruel, it's simply reality. The cosmos doesn't owe us multiple habitable worlds any more than Earth owes us perfect weather or inexhaustible resources. Mars colonization represents perhaps the purest expression of human exceptionalism, the belief that our species' needs and desires should override physical laws. But Mars teaches us that we are subject to the same constraints as every other form of matter and energy in the universe. The psychological appeal of Mars stems partly from our discomfort with being just one species on one planet in a vast cosmos. Mars colonization promises to make us multiplanetary, elevating human status from terrestrial accident to cosmic destiny. Yet this elevation is based on fantasy. We would still be one species, slightly more dispersed, living in technological bubbles that require constant maintenance and resupply. The fundamental reality of our cosmic insignificance remains unchanged. Perhaps the wisest response to Mars is gratitude rather than conquest. Gratitude that Earth exists as it does, with its protective atmosphere and stable climate and abundant water. Gratitude that we evolved on a world where simply breathing doesn't require technology. Mars reveals Earth's true value not as a launching pad for interplanetary expansion, but as an irreplaceable oasis in a cosmos largely hostile to life. Every sunrise that doesn't require artificial heating, every breath that needs no mechanical filtration, every drop of water that flows liquid at the surface represents a cosmic gift beyond price. The time, energy, and resources devoted to Mars colonization could address Earth's actual challenges, developing sustainable energy systems, restoring damaged ecosystems, eliminating poverty, curing diseases that affect billions. Instead of engineering solutions for hypothetical Martian problems, we could engineer solutions for real terrestrial ones. Instead of developing life support for dead planets, we could develop life support for our living one. Mars teaches us that the universe is vast, ancient, and largely indifferent to human survival. Most of it consists of radiation-scoured vacuum punctuated by chunks of frozen rock. The rare places where life can flourish naturally are precious, beyond calculation. In the end, Mars teaches the hardest lesson of all. The universe doesn't care about human ambitions. Planets follow physics, not desires. Gravity, radiation, atmospheric pressure, and magnetic fields operate according to laws that remain indifferent to our needs. And perhaps that's exactly the lesson we need to learn. In a cosmos that offers no guarantees of habitability, Earth's biosphere represents something precious beyond calculation, not a launching pad for interplanetary expansion, but a rare sanctuary to be protected with everything we have. Mars serves as a cosmic mirror showing us who we really are, a single species on a single planet, dependent on conditions so specific and fragile that they exist nowhere else we can reach. This isn't a limitation to overcome, but a reality to embrace. Mars is a laboratory of cosmic humility where we learn that the universe doesn't exist to serve human aspirations, and that this is perfectly fine. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.